So the Chinese developed this method of solving a system of linear equations a very long time ago. Um, but it takes the name of Carl Friedrich Gauss because he's the most recent, or he was the first European guy to develop this method, and he was trying to actually solve a system relating to the orbits of some kind of different celestial objects. I don't know, planets or something. So it takes his name. I guess he popularized it in Europe. And basically, the idea is um, you, uh, I'll show you how to symbolize this in the matrix and do the matrix operations and stuff. But basically, the idea is you get it so that one equation has z solved. So okay, we have this system of x, y, and z. You get z, and then you plug in z to another equation where it's just y and z, and you can use z to solve for y. And then once you have y and z, you plug in y and z into the equation where it's x, y, and z, and you solve for x. So it kind of unravels like so many dominoes to make some weird metaphors. Um, so the way you do it is, first let's represent this thing as an augmented matrix. So we'll write the coefficient matrix here: 2, 1, 1, -1, 3, 2, -1, 3, 2, and 1, 2, -1. And then let's write our constants here. It's the augmented part. Okay, so this matrix here represents the system of linear equations. We're trying to solve for x, y, and z. Oh my. And the way we're gonna do that is we're gonna shoot for creating a triangular matrix like this. So I'm gonna put this in blue to show that it's our goal. Where uh, essentially, so the constants over here will be whatever, but we'll just have numbers. Okay, so we'll have x, y, and z here, and then we'll have y and z, and then we'll just have z. So these will be zeros. So basically, in other words, I think of it as we'll turn off the x and we'll turn off the y, and we'll just be left with a z. So we'll be able to solve for z. And we'll turn off the x, but we'll have y and z. We'll use z to solve for y, and then we'll use y and z to solve for x up here. Hence, it'll unravel. So we're going for this triangular matrix. So it's sort of like, looks like a triangle. Okay. So the way we do that is we perform row operations until it is a triangular matrix. And I'm sleepy today, and I also am just not that great at row operations on matrices. So just bear with me if I kind of just stumble through this, even more than usual. But let's go for it. So we want to so basically we need to turn these things into zeros. And we need to do it in a valid way, just doing these row operations in valid ways. Um, and let's see. So there's three things we're allowed to do. We can swap two rows. That's not going to help us here. We can multiply a row by a non-zero scalar. You can't just multiply a row by 0. Just turn the whole row off. That doesn't get you anywhere. And you can add a multiple of one row to another. So let's see what we can do here. I let's first make this into a 0, because we can easily just add this row to this row, and -1 plus 1 is 0. So that'll take care of that. So let's concentrate on this column of making these things zeros first, and this one's gonna be the easiest. So let's okay, actually give me some room to indicate what I've done. So row 3 is now going to be row 2 plus row 3. So we can add two rows together. That counts. Okay. So we're just changing row 3. So I'm gonna write rows 1 and 2. So those aren't going to change. We're just modifying row 3 here. So we're adding the values of row 2 to it to get the new row 3. So -1 plus 1 is 0. All right, so we're doing good. 3 plus 2 is 5. 2 plus -1 is 1, and 11 plus 2 is 13. Okay. Um, Now let's make this into a 0. And then once these are zeros, we can keep modifying the rows, and these will just remain zeros. That's the nice thing about starting with that first column. Okay. So what we can do is actually add row 1 to it, but we've got to divide row 1 by 2. So we'll add a multiple of row 1, and that multiple will be 1/2. So -1 plus 1/2 of 2, which is 1, uh, is 0. So that'll be good. So so we're gonna modify that. This will be row 2 as it is plus 1/2 of row 1. Okay, and I'm gonna again write the rows that aren't changing this time around. So we're just modifying row 2. Okay, so what are my new values for row 2? So I'm taking the current row 2 values and adding half of row 1. So half of 2 is 1 plus -1 is 0. Yeah, we're on fire here. Half of 1 is 1/2 plus 3 is 3.5. Half of 1 plus 2 is 2.5. And half of 7 is 3.5 plus 11 is 14.5. Actually, I'm going to pause and check my work at this point. All right, I think we're okay so far. And it's nice to indicate the work you've done so you can kind of check your process. Okay, so these two are 0 so far. We need to make this a 0. So we need to somehow subtract 5 away from this row, or add -5 if you want to look at it that way. So what we can do is actually what we can do is this. Here's what I propose. I think it's going to be easier to think about these fractions if they're improper fractions, because I'll show you why. So 3 times 2 is 6 plus 1. So this is 7/2, and I'm just gonna delete this and rewrite 7/2, and then 2.5 be 5/2. And then 14.5 is going to, wait, 14, so 2 times 14 is 28 plus 1, so this is 29/2. Hope you're still awake. I think this is kind of a fun little puzzle. I wouldn't want to do this every day, but sorry if you do have to do it every day and you don't want to. If you want to, cool. Okay, the reason why I did that is, I could just multiply. Now it's easy to see if I just multiply this row by 2, which I'm allowed to do. I can multiply a row by a non-zero scalar. It'll make these into whole numbers again, which would be easier to track, at least for me. So row 2 is going to be 2 times row 2. I'm just multiplying it by row 2. So that's going to be 2 times 0 is 0. 2 times 7 halves is 7. 2 times 5 halves is 5. 2 times 29 halves is 29. So let me rewrite the matrix down here. Our row 2 became 0, 7, 5, and 29. And then we had 2, 1, 1, 7. And then we have 0, 5, 1, and 13. Okay, so what I would like to do ideally is I want to make this 5 into a 0, right? That's the last piece of the puzzle. I can't just multiply that row by 0. Not allowed to do that. But I can add it to a multiple of another row, and I can actually I can look at I can take a multiple of itself, a multiple of row 3. Okay, yeah. Here's what's going to happen. 5 and 7 have a common multiple, and that is 35. So say like I multiply this whole row by 7, and then I multiplied this whole row by 5. This would be 35, and this would be 35, and I could subtract them. So what I'm actually going to do is I'm going to multiply this whole row by negative 5, actually. So it's negative 35 plus positive 35. So negative 5, row 2. So I'm multiplying that row by negative 5. So 0 times negative 5 is 0. See how once these are 0, they just don't change. Negative 5 times 7 is negative 35. Now I'm just going to write this out. I'm not actually going to modify this row, but I'm going to write these values so that I can use them. So what is negative 5 times this row? So negative 5 times 5, negative 25. Negative 5 times 29 would be, well, 30 times 5 would be 150, but it's 29, so it would be 145, so it would be negative 145. Okay, and then I'm going to write out what would the values be if I multiply this whole row by 7. So 0 times 7 is 0, so this is 7. Alright, if there was a really obvious way to do this that's easier, I apologize, and good for you if you see it. 7 times 5 is 35. 7 times 1 is 7. 7 times 13 is 91. So yeah, 7 times 10 is 70. 3 times 7 is 21. Yeah, so 91. Okay, so I'm writing out these values because now I'm just going to say, I'm going to kind of rewrite the whole matrix now, and I'm going to say, actually I need more room. Oops. Okay, we're almost there. Hang in there. Okay. All I'm going to modify is the third row, because all the last thing that needs to happen is this needs to be a 0. So row 1 is good. Row 2 is good. So I'm just keeping these values handy. I'm not actually multiplying this row by negative 5 permanently. I'm just keeping these values handy because here's what's going to happen. The new value for row 3 is going to be negative 5 times row 2 plus 7 times row 3. Sorry, this should have said row 3. So I'm adding a multiple of one row to another, and kind of combining a step of I'm adding a multiple of another row to a multiple of this row. Okay, so So now, since I already did those calculations, I just add these values. So 0 plus 0 is 0. Negative 35 plus 35 is 0. Negative 25 plus 7 is, what is that? Negative 18. Negative 145 plus 91. I'm just going to do that on the calculator because my brain is uh, frying. So 91 minus 145, negative 54. Thank you. Thank you, calculator. Okay, so I've got this triangular matrix now. Um, and so, yes. So what? Okay. Yeah, so we're in good shape. So now let's reinterpret this matrix in terms of just these linear equations. So remember, these coefficients were for x, these coefficients were for y, these were for z. So what this is saying is simply, and I'm going to switch colors here, negative 18z equals negative 54. Okay? Well, divide by negative 18, divide by negative 18. What is that? I think that's 3, right? 54 divided by 18. Yeah. So z equals 3. We have our first winner. Z equals 3. Okay. Now this is saying 7y plus 5z equals 29. So we know z now. So 5 times z is 15. So 7y plus 15 equals 29. Minus 15 on both sides. 7y equals, what is 14? So y equals 2. See how we're just unraveling this thing like an onion? So we've got y and z. This last equation is saying 2x plus 1y plus 1z is equal to 7. Well, z is 3, y is 2, so 2 plus 3 is 5. Subtract 5 from both sides, 2x equals 1, or 2x equals 2, I mean. X equals 1. So x equals 1. And we know we're right because I actually set it up so that x would be 1, y would be 2, and z would be 3, just to simplify things. Believe it or not, this is a simplification. Okay, so that's the method. This has gone on way too long. I hope you enjoy solving via this method that Gauss came up with centuries after the Chinese, and it's pretty slick, but maybe you can come up with a better way. All right, peace.